Okay, so I'm going to go ahead and do a brief review on curvature and tangential and normal components of acceleration. Um, like I said earlier, I don't think these are on the test, but they were technically on the list of sections that was given before spring break. So we'll see if I don't think it's on there, but we'll see. Yeah, okay. All right. So for curvature, if we have a curve. Uh, If we have a curve, we can talk about the tangent vector, okay? And the rate at which this tangent vector is turning is the curvature, right? So it's the rate at which this tangent vector is turning. Now, just to make sure that all things are equal, we're going to be doing this derivative with respect to the right. We want this to be evenly spaced as our units, right? We don't want this to be slowing down or speeding up as it's turning. Okay, so here this is going to be units of s. Okay, so s is evenly spaced. There's nothing slowing down or speeding up. It's just turning if it's turning at all. Okay, so the curvature is going to be the norm of dt, right, the tangent vector, ds. And it's actually the unit tangent vector. Um, like this. Okay, so what is dTds? Well, we can use the chain rule for that. So typically we don't have this curve in terms of s, right? We don't have it in terms of evenly spaced things. We have it in terms of t, like time. So again, I can think of a particle here moving along this curve. It would be nice if I had, this curve given to me in terms of, um, you know, evenly spaced units in terms of uh, position along this curve, but typically it's given in terms of time, right? So what is the position at a given time? So we want to write this tangent vector in terms of, we usually have it in terms of t, so we want to write the derivatives in terms of t. So I can use the chain rule, and that gives me dt times dt ds. Okay, so this is a vector, this is a scalar. I can bring it out in front if um, if I take the absolute value, like this. And here, this I can write as 1 over ds dt. And the derivative of the unit tangent vector, you guys should recognize that as the normal vector. Okay. Um, so this on the bottom, ds dt, that's the rate of change of position with respect to time. So that's going to be 1 over r prime of t. And here, this is right, it's the normal vector. I'm going to write it actually just as the derivative of the unit tangent vector. That's a little bit easier to see. Still kind of hard to see. Let me just rewrite it. The unit tangent vector, the derivative of that, divided by the derivative of r prime t. Okay, I'll do a working example using that in a little bit. Where did my cursor go? Okay, so some of the other formulas though that we have is we derive this other one. So this is the curvature, right? These are all the curvature. They all represent the same thing. Another expression that we had that didn't involve finding tangent vectors or unit tangent vectors, if I just have a curve r of t, then the curvature of this is going to be the norm of r prime of t cross r double prime of t over, so this is norm, I guess it should be norm. Okay, over the norm of r prime of t cubed.
Mic off. Mic on.
So this is useful when I don't want to have to compute tangent vectors, and I just have r, and I can take the derivative of that, and that can make things quite a bit simpler. Okay, let's see. So find the curvature. So here's an example. It says find the curvature of r of t is I plus tj plus t squared k. All right, so I'll do it using both of these. So first I'll do this one. So the tangent vector is going to be, so that's going to be 0 plus 1 plus 2t, okay? And then I need the norm of this so I can find the unit normal, the unit tangent vector. So the norm of the tangent vector, that's going to be square root 1 plus 2 squared. That's root 5. And that tells me that the unit tangent vector, sorry, not the derivative, the unit tangent vector is I'll go to component form, 1 over root 5, 2 over root 5. Okay, so now for this I want the derivative of that. Okay. Oh, and real quick here, this the norm of t, right? That's the same as the norm of r prime of t, right? Because the tangent vector is the same as just r prime, right? That's what we did. We took the derivative. Okay, so we take the derivative of this. There should be a t right here. Okay, so I take the derivative of this, and I get 0, 0, 2 over root 5. So the norm of that is just 2 root 5. Okay, so finally, using this formula right here, I have that the curvature is equal to 2 over root 5 over root 5. So I multiply the bottom by 1 over root 5 times 1 over root 5. Those cancel, and I get 2 over 5. And that's the curvature. So it's the derivative of the unit tangent vector divided by the derivative, or the norm of the derivative of r. Okay, so I'm going to do the same example, but this time I'm going to use this formula. Okay, so r prime of t, that's just the derivative, that's going to be 0, 1, 2t. I need r double prime 0, 0, 2. And now I want to do the cross product of these two. Um, so I have r prime cross r double prime. Um, so what is that? If I set this up, I, j, k, I have 0, 1, 2, t, 0, 0, 2. So I'm going to have, let's see, so that's, I cross this one out. It's going to be 2 minus 0. And then I have cross this one out. I have 0 minus 0, that's 0. Cross this one out, I have 0 minus 0. Again, that's 0. Okay, so the norm of r prime cross r double prime is 2. All right, that looks like a good start because I still need the norm of r prime cubed. So um, did I make a mistake? I think I made a mistake in this top one. I did. This was supposed to be 2t. Good boy. Okay, so that would have changed this quite a bit. So I'm going to say that the rest of this was actually wrong. Sorry about that. Um, because I would have had to divide this by 1 over 2, let's say 1 over, or I would have had to divide this by square root of 1 plus 4t squared, and then do the derivative of that, which kind of would have been a pain. Actually, no, it definitely would have been a pain. But that's an example of where I would use this formula because it's a lot easier. So I need the norm of r prime. So norm r prime of t, that's going to be square root 1 plus 4t squared. Okay, so the curvature, that's this divided by this, cubed. Okay, it needs to be this cubed, right? There's a cubed up here, right? This cubed. So that's going to be 2 over 1 plus 4t to the 3 halves. That's what it should have been. And so, yeah, this is definitely made a mistake up here. And that was the mistake right there. Okay. Those are really the two formulas you need to know about curvature. I don't think we're going to be doing much else with that. Um, so the next thing I was going to talk about was the components of velocity and acceleration. Okay, so um, let's think of r as being position. So then r prime is velocity, and that's also going to be called v. So that means that the norm of r prime, that's going to be the speed, right? It's not a vector, it's just the speed. And then r double prime, that's the acceleration, which we'll also call a. Okay, so if we're going to be interested in this acceleration right here. Okay, so when something is accelerating, there's two ways that could happen, right? It could be accelerating because so acceleration is when the velocity vector is changing. So it could be accelerating whenever it's curving, even though it's not speeding up. Okay, we say it's accelerating because the velocity vector is changing, right? So if it goes from here to here, right, the velocity vector changed, it accelerated. It could also accelerate if it's speeding up. So maybe this is the velocity vector here, and up here, it's still pointing in the same direction, but maybe it's going a lot faster or a lot slower. Okay, it would have accelerated kind of in a straight line. It's sped up. So there's two types of acceleration, right? You either accelerate because you're curving, or you accelerate because you're speeding up. And we want a way to kind of separate these two and figure out, see what part is what. Okay, so what do we know? We know that the unit tangent vector, that's r prime divided by norm of r prime at position t. Okay, but if I solve for this, I have r prime of t is equal to the norm of r prime times the unit tangent vector. Okay, that's fine. So let me just point out that this right here is the speed. I'm not going to put a vector over it because it's a scalar speed times the unit tangent vector. And here this is the velocity vector. Okay, so now let's look at the acceleration. So the acceleration, that's the second derivative. That's the derivative of this with respect to t. So I'll have to use the product rule. So I have r double prime is equal to, so this is going to be the derivative of the speed times the unit tangent vector plus the speed times the derivative of the unit tangent vector. Okay, so I can write this as the in terms of the unit normal vector, right? So I know that this is v prime t hat t plus speed times the normal vector. Okay, and let me just normalize the normal vector, right? So we have the unit normal vector. So that's going to be v prime t plus, that's going to be v times the norm of t hat prime times n hat. Okay. Um, oops, that's not norm. No, that is norm. That is norm. Okay, so one last thing. I'm going to write this in this. I'm going to use the curvature formula from up here. This one right here, like this. So if I multiply and divide by the norm of r prime, I'm going to multiply and divide by the norm of r prime. V norm of r prime times t hat prime over norm of r prime times n hat. So we know that's the curvature, and we also know that norm of r prime, that's the speed. So finally, this gives us what? This gives us v prime t hat of t plus v squared times the curvature times n hat. Okay, so these are the two components of acceleration. So this is the tangential component, right? This is the rate at which your speed is changing. So this right here tells us, are we speeding up or are we slowing down? It doesn't tell us if we're turning or not. It just tells us, is our speed at which we're moving, is that changing? And this term over here, this is going to tell us how much are we accelerating because we are turning, right? It doesn't really tell us if we're speeding up or anything, but it tells us how much are we accelerating because we're turning. So one more interesting thing about this is that this term right here, so if we recall from the curvature, well, our interpretation of the curvature, if I have some curve, the curvature at a point, so if I kind of find a circle that kind of best fits the curve, so kind of the the curvature is going to be 1 over the radius. Okay, so we can kind of think of the curvature as kind of 1 over the radius at the spot of whatever circle we're kind of traveling on at the moment, right? It's going to change. Over here, I would have a much smaller circle than I do over here. And actually, this circle is probably too small. But notice what that gives us here. So here, this is the derivative of our speed. That's the rate at which we're changing our speed, right? Speeding up, slowing down. But this, we have something that looks v squared k. So if this was a circle, this would be something like v squared over r. And if you've taken physics, you should recognize this as the centripetal acceleration, right? So this is the acceleration that you get when you're moving around in a circle. Okay, I don't think there's much else to say about this. I would know this. That's not hard to forget. You don't need to. You shouldn't need to know how to drive it. And these are the two formulas that you should know for the curvature. And then just as general knowledge, I would be very happy if you remember the actual definition being that one. But again, to summarize, I don't think that this stuff is going to be on the test, but just in case, there you have it.